Aquaporins are channels specifically for water. So there was a man, his name was Peter, A-G-R-E, Agre, I guess. I'm not really sure how you pronounce it. But he was doing an experiment that you did in lab. He's looking at red blood cells and their permeability to solutes. And what's the concentration of solute inside a red blood cell or any other cell in your body? 0.3 molar or 300 milliosmolar. This is the same thing as 0.3 molar. But usually we talk about osmolar when we're talking about the human body. The solutes that he was looking at, very similar to what you looked at upstairs. He saw the same thing that you did when you put propanol or propyl alcohol out here. Is there going to be propyl alcohol in a red blood cell? Doubt it. Especially when you see what happens when propyl alcohol gets in touch with red blood cells. Oops. Okay. So, 0 out in there, and we had a 3 molar solution outside. So 3 molar propyl alcohol to 0.3 molar inside. Where's the concentration gradient? To go into the red blood cell or out of the red blood cell? In, obviously, is 3 molar to 0. So propyl alcohol is going in. Propyl alcohol does not lyse the red blood cell. What lyses the red blood cell? Water lyses the red blood cell. So 3 molar solution of propyl alcohol, it rushes in fast, increases the internal osmolarity faster than the red blood cell's membrane can pump solute out. So you create a huge gradient for water to enter. How fast did propyl alcohol blow up a red blood cell? It was fast, but how fast? Faster than that. Like 3 to 5 seconds. Boom! If you weren't watching, you put the blood in, you're swirling, did you start? And you look back, it's lysed already. It goes that fast. He's scratching his head. If water is tumbling through the plasma membrane and going through leak channels, how can it lyse? How can propyl alcohol pull water in by changing the concentration of solutes in there? How can it do that? Get the water moving that fast through the plasma membrane. So he went out in search of the aquaporin. He found the first aquaporin, and he got Nobel Prize and $1 million. Woohoo! Just from a simple experiment like you were doing in lab. So aquaporins, they're either in the membrane all the time, or they're upregulated when the cell needs them. Everybody understand what upregulation means? No. Nope. Okay. So when a cell doesn't need a channel or another protein, pulls it out of the plasma membrane, apical plasma membrane, or wherever else it might be located, pulls it into the cytosol and just keeps it there for when it needs to have it in the membrane. So when it pulls it out of the membrane, that's called downregulation. When it inserts it back into the membrane, that's called upregulation. So from the inside of the cell to the membrane, up. And when you take it out of the membrane, pull it inside, then it's downregulation. Cells will up and down regulate receptors, channels, other things that they may or may not be using proton pumps. Don't think they up and down regulate ATPases, but they might. I don't know of anything offhand where an ATPase is up or down regulated, but you have certainly receptors for hormones. The cell doesn't want to be overstimulated because it would get fatigued and maybe die. So for self-preservation, it will prevent itself from being overstimulated by pulling hormone receptors out of the plasma membrane. So it has its normal, maybe normal elevated metabolic rate, but not super elevated to the point of fatigue. When hormone concentrations are low and it's not getting the stimulation it needs, upregulate receptors so these sparse hormones have a chance to bind to the receptor and the cell can be stimulated at the level it wants to be stimulated at. So for self-preservation, up and down regulation. Aquaporins, you usually find those in the upregulation and downregulation happening in your kidneys. If you're drinking a lot of water, do you want to reabsorb that water? No, you want to get rid of it. And you find out you do get rid of it because you use the bathroom a lot. When you're dehydrated, do you want to reabsorb the water that you're filtering that might go out as urine? Yeah, because you might not get water for a long time out there in the desert. So your kidneys are designed to take the blood to the areas of the kidney where we can reabsorb water to the max. And then upregulate these aquaporins so we can get as much water back into the systemic circulation as possible. So there'll be hormone that will come out and tell the kidneys upregulate aquaporins so we can get back the water that got past the filtration unit. The osmosis, when you see that term, remember that's referring only to water movement, but solute influences water concentration. If you have something that is 3 molar, it's referred to as hyper something. If you see hyperosmotic, you know that there's more solute out here than water with respect to your normal concentration in your red blood cells. The term osmotic tells you water is going to move. You don't know anything about the particle. The first thing that's going to happen, water is going to move. Where is water going to move first in this scenario? It's going to go out. So the first thing is water leaves the red blood cell. If you've got propyl alcohol is going in fast enough to build up the solute concentration in here, so you create a water gradient. Was initially out, but now it's big time into the cell, and so much water goes in that the cell explodes. So if there's a checklist, a scenario like this, first thing is water leaves the RBC. Yeah. Guess that's as far as I'm going to get it to go. RBC. Second thing happens is propyl I don't have to say propyl. I know it's alcohol. Propyl what? Enters. Third, just to make sure, solute concentration in RBC increase solute concentration in RBC for decreased what in RBC?
Water.
Decreased water in RBC. So if you want to put brackets, that means concentration. So then number 5. Okay, water enters. And last thing that happens, lysis. Certainly with propyl you get lysis. There might be something that is lipid soluble that moves in slow enough that it takes a real long time for lysis to occur, so you might not have seen it in lab. Let's make another cell here. So solute concentration is in a normal cell is 0.3 molar, 300 milliosmoles. So red blood cell put into glucose. Let's put, what was it, 0.5 molar glucose that was in lab. If you're not in lab, you still pay attention because this might be on the exam. Exact same question. So we got 3 milliosmoles in, 300 milliosmoles or 0.3 molar. Got 0.5 molar outside or 500 milliosmoles outside. What's the first thing that's going to happen to my cell?
Water is going out.
Water's going out because you got 500 particles out here and 300 particles in there. Yeah, less solute here, so more water inside than outside. Okay. Is there glucose in a red blood cell to start with?
No.
Probably not. Why?
Does it need energy?
Because it's using glucose, breaking it down into 3 carbon units to get ATP. So there's probably 0 or close to 0 glucose inside because the red blood cell is using all the glucose. So is there a gradient for glucose to enter? Yes. Will glucose concentrations change the 300 milliosmoles here? No, because it's getting converted to ATP.
Yes.
Okay, so glucose is acting as though it's non-permeable. It does go in, but it's being consumed, so it's acting as though this solution is hyper, what's the word that is stick here? Tonic. So it's acting as though it's not penetrating, but it actually is. So it's not lysing the red blood cell because it's being consumed. So what happens to the red blood cell when water continues to lead towards this 5.5 molar solution? Crenate. So it starts to shrivel. And when it shrivels, what happens to its specific gravity? It gets hollow. It gets heavier. So its weight goes up and it starts to sink. Something else happens in 0.5 molar glucose. Crenated red blood cells start to, what's that? Agglutinate. They start to stick together. When they stick together, what happens to the specific gravity? It increases even more, so they start to precipitate faster. So you look at your test tube, you had this opaque solution, and then eventually the top layers start to get clear and more clear and more clear, and you start to develop a pellet of red blood cells in the bottom. What happens if you vortex? Resuspended. So this is not a permanent agglutination, it's only temporary.
Is the cremation permanent?
The crenation is permanent. As you continue over time to consume glucose, then what's going to happen to if glucose is disappearing into the red blood cell and getting consumed, then the solution out here is becoming less hypertonic. At some point, water is going to start to enter again, because as soon as this gets below 0.3 molar, then water is going to start to enter again. So if you leave the red blood cells in this glucose, they precipitate out. You can temporarily resuspend them. They precipitate out. Eventually, if you keep doing this resuspension, when the glucose concentration outside gets below the other solute concentration in there, then water re-enters and the cell can go back to its normal shape and float again. Will red blood cells always be in solution? Once, if this was 0.3 molar, and you just put the test tube in the rack and waited half an hour, would the red blood cells still be in suspension? No, because by definition a suspension is temporary, right? Gravity is going to pull those cells out of solution. Okay, we've got 100% water to the left, and we've got water and solute on the right. So it's telling you 100% here, 10% solute, 90% water. The solute here is dissolved in the water, so you see through. Might not be clear like water, but you can see through, so it's translucent. And that's the definition of solute. Now we put the two chambers together and separate side A and B, or side 1 and 2, by a semi-permeable membrane. We've got the same scenario as with the separate beakers, 100% water to the left, and 10% solute in water to the right. So we're looking first, they mention osmosis. So the first thing you look for is the influence of the solute concentration on water movement. So water always moves first. You always look for water to be moving if there's a concentration gradient. Here, water, there's less water on side 2, so water will move to the side 2 until the pressure of water movement across due to osmosis is balanced by the hydrostatic forces, and that includes gravitational forces pushing down here. When those forces can balance the tendency for water to come to side 2, then diffusion, net diffusion, will stop. So you still have pure water here, but water is now in a higher concentration in side 2. What happens to the solute concentration? Goes down. So even a non-permeable solute, its concentration can still change. So if we had a beaker if I can figure this out in my head. Okay, now we have 2 molar sodium chloride, 1 molar glucose. What happens to the 2 molar sodium chloride when it hits water? Disassociate. Assume, for question purposes, full disassociation. How many moles do I have on side A? So this has now become a 4 molar solution. Side B, is there any change? No, because glucose has covalent bonds. So no, I'm not telling you anything but that. What's the first thing that's going to happen? Water moves. Yeah, 1 mole here and 4 moles there. So big time water is going towards A. So it goes from B to A. So anything else moving? I didn't say sodium was permeable this time.
Water is moving.
Water moves.
Water continues.
So what happens to the concentration of sodium?
Goes down.
Decreases. It's not moving, but water is going towards it. The more water is in between sodium molecules, so water concentration goes down. What about chloride?
Goes down.
So decreased concentration of chloride. Again, chloride is not leaving side A, but water is coming towards it, so its concentration goes down. What about glucose? So I heard a lot of buzzing, but nothing intelligible. So what's happening to glucose? Water is leaving, so its concentration goes up. But even though the solute is not permeable, when water leaves or comes into its vicinity, its concentration can still change. So think beyond what is told. Yes, water moves first. Yes, no further solute is moving because you weren't told that solute could move, so you can't make up your own question. Answer based on what was given to you. Solute is now non-permeable. The membrane is still semi-permeable, but just to water. So water left, went to sodium and chloride, so their concentrations go down. They didn't leave. That's not why their concentration is going down. Their concentration goes down because water came to them. And the water left glucose, so its concentration goes up. Okay, so osmosis, water movement, maybe something is hyperosmotic, and that means you don't know about the particle. Could be permeable, could not be permeable. If it is hypertonic, you know it's non-permeable or acting as though it's non-permeable. What else acts as though it's non-permeable besides glucose? Sodium. Because sodium, if it enters, what happens to it? It's pumped back out because you got the ATPase that will pump it back out. So it acts as though it's non-permeable. So membrane permeability. We've got water in higher concentration here because we've only got 2 solute particles. In side 2 we've got 4 solute particles. So the first thing that happens is water moves from side one to side two. If solute is permeable, then the next thing that happens is solute moves from side two to side one. How many solutes go to side one? One. Because then it's reached equilibrium. But since solute left side two and went to side one, what's the third thing that happens? Water goes back to side one. So you have water moving first, down is concentration gradient. Where is water in lowest concentration? Where solute is in highest concentration. That happens first. Then solute will do its diffusion. So if you have a ratio of 2 to 4, then only 1 can go to side 1, from 2 to 1. So that is enough to then make water concentration higher than it was previously in side 1. So now water can return. Diffusion still goes on beyond that point, but net diffusion has ceased. So what happens to solute concentration in side 2? It went down. What happened to solute concentration in side 1? It went up. Okay. Why isn't it making noise? Volume on.
The computer's on.
It says it's on.
It's a little speaker icon.
This one?
Yeah.
Ew.
Concentration to the area with the lower water concentrate. Imagine a container divided by a membrane that is permeable to water but not to proteins. We can pour water into the left compartment and the same volume of protein-rich solution into the right compartment. As you can see, the right compartment has a lower concentration of water molecules. Proteins take up some of the space. Water molecules can move in both directions, but the net diffusion of water in this example will be from left to right, from the area with the higher water concentration to the area with the lower water concentration.
That's all you're going to say? Okay, well that was, let's see if there's another one then. Oh, I know what that's, 3D animation. Let's see if I can pull that up.
Solution A is separated from solution B by a semi-permeable membrane. The membrane is said to be semi-permeable because it allows water to pass freely, but restricts the movement of larger solutes between the solutions. Both solutions share identical osmotic potentials, equal concentrations, and are therefore isotonic to one another. This state is known as equilibrium. Let's see what happens when we increase the concentration of solution B. The more concentrated hypertonic solution B is now said to have a more negative osmotic potential than the less concentrated hypotonic solution A. Water, driven by the difference in osmotic potential, moves toward the solution with a more negative osmotic potential. Therefore, the water in solution A will proceed toward solution B until equilibrium is reestablished. The net movement of water is osmosis.
Did they confuse you by saying negative osmotic force? Okay, actually what they're talking about being negative is lower water concentration. So it's negative, this is positive. Positive has traction, I guess if you want to call it, towards the negative. It's going down its concentration from the higher to the lower. So it's not counterintuitive, it's just a different way of saying that. So you want to think of negative as sucking water towards it, or just think of it as having since it's below zero, it's going to have a lower amount of water, and the side that has more water will then be moving towards it. So osmolarity. We're always talking about molar solutions. Yes, in lab there are molal solutions, but we're talking about molar solutions. Osmolar because it's just a small part of a mole. And nowhere in our body do we operate with molar concentrations of any solute. Osmolarity is dangerous because it tells you nothing about the solute particle. It may be non-permeable, but it may be permeable. So if you're going into the medical field, you don't want to mess with anything that says isoosmotic. If it says isotonic, that means the solute is either non-permeable, doesn't cross, or it's acting as though it's non-permeable. Typical isotonic solution that EMTs will give, people in the hospital will give, is isotonic saline. Got sodium and chloride in solution, put it in an IV, the sodium crosses, but it's pumped right back out. The chloride crosses, it's pumped right back out. Another would be glucose. There's dextrose saline. So the concentration of glucose, which is dextrose, one of my TAs didn't know, you don't have any glucose downstairs. I said, yeah, it does. It's called dextrose. Ooh, it's dextrose and levulose. They're both glucose. Anyway. So you have glucose. It also acts as though it's non-permeable, goes in and it's consumed. So it either goes in and it's pumped back out, goes in and it's consumed, or can't get through the membrane at all. Then you have isotonic. Tonicity, you always feel, thank you for telling me tonicity, because now I know non-permeable or acting as though it's non-permeable. Isosmotic, you could kill somebody. Yes, initially it's not having water move at all because it's iso. But if the particles can penetrate, they're going to create a gradient for water into your cell, and that could cause lysis. So tonicity, good to know. It tells you particles are non-permeable. Osmotic, isosmotic, only tells you about water. Okay, so we have a solute that is, we have a membrane that is permeable to water, but impermeable to solutes. So side 2, how would you describe it with respect to side 1? Solute concentration is higher, and the solute is non-permeable. Hypertonic. You got more solute inside 2, and that means you have less water. You have more solute that's non-permeable, so you have a hypertonic solution. If I asked you to compare side 1 to side 2, how would you describe side 1? Hypotonic, same solute. Okay, so all that can move is water. Here the membrane slides, changes position based on volume. Sometimes the volume would have to go up because the membrane doesn't slide. But here the membrane slides for some reason, magic kind fancy stuff. Okay, so started in the middle, but what happens, where's water going to move? From 1 to 2, so water goes to side 2. Now the volume in side 2 goes up, which pushes your membrane to the left, and now your volume on side 1 is smaller and volume on side 2 is larger. Kind of strange way to illustrate it. I don't think there's anything in any lab that actually does that. Maybe with plunger systems, yeah, but anyways. So tonicity, isotonic. Is there a gradient for water to move? No. So iso is telling you water is concentrated same on both sides. The solute that's in the water is, if the solution was outside a red blood cell, what would the concentration of that solute have to be outside the red blood cell? Okay, we got an isotonic solution. And I asked you, what concentration does this isotonic solution have to have so there's no water movement across the cell membrane? 0.3 molar or 300 milliosmoles. Just try and get used to thinking. You can translate back to molar, but think osmolar. So most cells are going to be operating at 0.3 milliosmoles. So isotonic means you have a non-penetrating particle in the same amount of water that's inside, and so solute concentration must be at 300 milliosmoles. Hypotonic, give me a number that's hypotonic. So 200, or anything that's less than 300. What is hypertonic? 400, anything that's greater than 300, you get into hyper, and this would be hypo. Okay, hypo. Okay, iso, hypo, and hypertonic solutions, are they the same as iso, hypo, and hyperosmotic solutions? Might be, but you don't know. Which one don't you want to see on the bag? Osmotic, because you don't know about the permeability of the solute. Okay, so we got a red blood cell, and we put it in solution of non-penetrating particles. If the particles are at 300 milliosmoles, then nothing happens. Red blood cell keeps its biconcave shape, and eventually it's going to precipitate out, but in the meantime, it's going to stay in solution far longer than if it's put into a hypertonic solution. Why? So the cell shrinks or crenates. What happens? Why is it going to not stay in solution as long as a normal red blood cell? As it gets heavier, and so it's going to sink faster. When you put it in a hypotonic solution, what's the danger there? Sorry. It could lyse. So here the membrane is swelling, but no lysis has occurred. There's still a little dimple there. This is a sphere now. If you continue, if water is still going in, at some point the cell might lyse. So red blood cells and all other cells, they have a capability to move solute out. So if you put them into 200 milliosmoles of a hypotonic solution at 200 milliosmoles, they may survive because they can move enough solute out so that inside they become less concentrated in solute. So they're going to get less, they're going to have less water coming in because now their water concentration is higher. So move solute out, get the water concentration up a little bit, and then there's less of a gradient for water to come in. So they may become spherical, but they don't blow up. What would be a sign that lysis occurred? The water, is it going to stay looking like water? It's going to turn red. Because what's inside the red blood cell? Hemoglobin is going to go into solution. So when the water turns translucent red, then you're going to know that lysis occurred. One other thing, normal red blood cells will, and even swollen red blood cells, they stay in solution longer because their specific gravity is less than the crenated red blood cells. So while the crenated red blood cells are going down, the others stay in solution. When they stay in solution, you can't see through the solution. What the light is refracted too many times, you can't see something that's on the other side of that solution. But let the membrane blow up, the membranes go down to the bottom, you can't see them anymore, they're referred to as ghosts. Then freeing up the hemoglobin, the water turns red and you can see light through it. Okay, facilitated diffusion requires a carrier. Active transport also requires a carrier. Difference is facilitated diffusion is diffusion down a concentration gradient. Active transport is up the concentration gradient. Active requires ATP used directly by that transport protein, not somewhere else in the cell, but by that protein, and that's going to be active, not secondary active transport. Some facilitated diffusion, if the concentration gradient is being maintained by an ATPase, then you call it secondary active transport. If the facilitated diffusion is operating post-meal, glucose concentration goes up, and so facilitated diffusion of glucose into cells goes up because glucose is higher outside than inside, then it's total passive facilitated diffusion, no secondary active transport attached to that description. The carrier proteins are said to flip in the membrane. If you think about it logically, they can't flip because they got hydrophobic components that have to be in association with the lipid, and you've got hydrophilic areas inside and outside, and you can't flip them through the plasma membrane very easily. So they must be changing their shape so that you facilitate the movement of that particle in. But actually, flipping, not going to be happening. Okay.
The distribution of sodium and potassium ions across the neuron membrane results from both passive and active transport of these ions. Some sodium ions leak from the interstitial fluid into the neuron cytoplasm through channel proteins. The sodium-potassium pump actively transports sodium and potassium ions. It moves 2 potassium ions into the cell for every 3 sodium ions it moves out. Some potassium ions leak into the neuron through channel proteins. More ions leak out. When the neuron is at rest, the total inward and outward movements for each kind of ion are balanced. Pumping and leaking processes maintain concentration and electrical gradients across the membrane.
Okay, kind of beat that to death. So let's look at the carrier process for glucose. We've got a protein in the membrane. It's got a binding site for this solute. So if this is glucose, it can bind one glucose, and that's done. Then the protein changes shape. It closes on the outside, opens on the inside. Since the solute is in lower concentration inside, it diffuses off the carrier and enters the cell. Once the solute has left, then the transporter goes back to its original shape, and it's ready to transport again. So this, we have a GLUT1 or glucose transporter 1 that works like this. Binds glucose when glucose is in high concentration outside. It won't be likely to bind glucose when glucose is low because glucose has to diffuse in there and bind to the active site. So more likely going to happen when glucose concentrations are high. If an occasional glucose gets in there, it will be transported into the cell. Higher the glucose concentration, more likely it binds. Then once it's bound, then the protein will change shape and the molecule will diffuse down its concentration gradient. What happened to my animations? Okay. Nope.
In this animation, the blue balls represent glucose. Since glucose is more concentrated on one side of the membrane compared to the other, it will move down the concentration gradient by passive transport. However, since it is a polar molecule, it will not pass through the membrane freely. In order to cross through the membrane, each glucose molecule will have to bind to a specific integral protein in the membrane, called a carrier protein or transport protein. Since the passive transport of both ions and polar molecules requires transport proteins, this method of molecular transport is called facilitated diffusion. As glucose binds to the transport protein, the protein changes its shape, or conformation, which directs the movement of glucose down the concentration gradient. Note that when the glucose is released and the binding site becomes available again, the transport protein resumes its original shape. This process of facilitated diffusion will continue until the concentration of glucose is equal on both sides of the membrane.
Most cells, that's not going to happen. Glucose is not going to...
Let's check what you have learned. Consider the concentration gradient in this graphic. Then, click the arrow that indicates the net movement of glucose through this glucose transporter.
Into or out of the cell? It'll say, you're right.
That's correct. Passive transport moves solutes down the concentration gradient.
Okay, real true cells. Is glucose concentration inside the cell going to build up to and get to equilibrium? No. It's either going to be used or it's going to be turned into glycogen. And when it's turned into glycogen, it's no longer glucose. It is glucose, but there's a covalent bond between the glucose molecules, so it's not glucose anymore as far as concentration gradients. are concerned. Okay, so let's see. Okay, so primary active transport, secondary active transport. Primary active transport, that protein uses ATP. Secondary active transport does not use ATP. It uses the concentration gradient of some ion, like sodium. If it's using sodium and the gradient is maintained by the active transport, that primary active transport, then whatever sodium is moving is said to be brought in by secondary active transport. If something is moving two things in the same direction, like sodium and glucose, you call it a symport. Sym meaning together, in the same direction. If it's like the ATPase pumping sodium out and potassium back in, then it's an antiport. Some facilitated diffusion, which is totally passive, will pump something out and bring something in, so it's an antiport. If it's bringing two things in with no ATP consumed by the transporter, then it's a symport. So Wednesday we'll pick up with the symport.